Make a long story short, I did the calibration on that engine, and at full throttle, at red line, which was 9,600 RPM, there was a 20% difference in fueling between the two cylinders. So we're talking full throttle, 9,600 RPM, under boost. The vehicles were turbocharged at the time. 20% difference between cylinders that needed to be corrected.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Paul Yaw from Injector Dynamics. Now, the injector really is one of the most critical elements when it comes to tuning your engine and getting the best performance as well as the most reliability and consistency out of that tune. For many years, there was a significant lack of knowledge around exactly what the injector did and how it functions. Now, I'm sure you're thinking, well, it opens and it supplies fuel to the engine. Well, yes, that's true, but when we start getting a little bit more granular in what the injector does and how it actually operates, there is a huge amount more to it that we really need to understand. We also need accurate data about the characterization of the injectors, or in other words, how they function, that we can put into our engine management system when we're tuning it, irrespective whether that's a factory or aftermarket engine management system. This is going to streamline the tuning process, and in some instances, not having this accurate data can make it difficult or even impossible to tune the engine properly. In my opinion, Paul and Injector Dynamics are really responsible for lifting the veil off some of these aspects of fuel injector performance and really bringing the level of knowledge and understanding of the whole industry up several notches. It's also forced the rest of the aftermarket fuel industry to play catch up. This is a wide-ranging chat with Paul, and at this stage, one of our longest podcasts. So there's a huge amount of information to take in. We get down in the weeds with injectors, how they work, how to choose injectors for your particular application, when an injector is too small or too big, what sort of maximum duty cycle you should be running. We destroy some of the common myths and misconceptions around how the injector actually operates. Before we jump into our chat with Paul, though, if you are new to High Performance Academy and the Tuned In podcast, HPA is an online training school. We specialize in teaching people how to tune engine management systems, build performance engines, construct wiring harnesses. We also cover race driver education, race car setup, optimization, data analysis, and fabrication. You can find all of our courses at hpaacademy.com/courses, but I think really relevant to today's topic is our EFI Tuning Fundamentals course. This course, as its name implies, will teach you the fundamentals behind how an EFI engine operates. You'll learn how the engine itself operates as well as what the ECU is actually doing, how we should be using the ECU to control our fuel delivery and our ignition timing. We dive deep in this course into some of the topics that we'll be discussing today, such as injector characterization, injector latency, or dead time, just to name a few of the topics. If you are interested in learning more about that course, we'll put a link to it in the show notes. And as an HPA Tuned In podcast listener, you can use the coupon code podcast75. That'll get you $75 off the purchase of your very first HPA course. Again, we'll put a link in the description. All right, with our introduction out of the way, let's get into our interview now. All right, welcome to the podcast, Paul. Thanks for joining us today. Now, I'm interested, as we normally like to get started with these interviews, to just learn a little bit more about your background. I think I've known you for about a decade now, and I still actually don't know the full story on how you got involved in the auto industry. So take us back.
It's like most kids, I was interested in cars. And I had a plastic molding business in the middle of, doing what I was doing to make a buck. I was working on race cars there in the shop as well, because that's what I truly enjoyed. But the plastic molding business was profitable. It was working well for me. Thankfully, I developed an allergy to a number of the chemicals that I was working with. Some epoxies have a quality that makes you potentially develop a sensitivity to them over time, right? And I did. I thought my allergies were just getting worse. It wasn't seasonal allergies. It was those chemicals. I was already working on some race cars in the shop, and one thing led to another, and I just transitioned between the two. So for years, I was working on cars with tools that had bits of plastic stuck on them and things like that. That's how I went from not working on cars to working on cars. That's the short story. And quite frankly, the rest of it, I think, is probably pretty boring.
Okay, let's get an understanding of your educational background. I've talked to you a lot about injectors and just about anything else engine related, and you sort of operate at a very high level and you're very data driven. Where does that come from? Is there a sort of formal qualification background that got you to this point, or is this just how you put together?
A bit of both. I've always been interested in understanding how things work. I find that my 8-year-old is exactly the same. So some of that's genetic. I did go to school for mechanical engineering and dropped out partway through because it was interfering with my drugging and drinking and girl chasing. So I ended up with no degree, half an education, and a desire to work on race cars. So can I say that on your podcast?
Well, you've said it now, so we can't take it back.
There you go.
I mean, that's the truth.
Yeah, I mean, essentially that's it. What I did gain from the education, or the half of an education, I should say, is the understanding that there is an answer to nearly everything if you just look in the right book and understand the concepts well enough to be able to work your way through it. I mean, at the end of the day, when we're working on race cars, almost everything comes down to physics. I mean, we have thermodynamics, we have chemistry, but ultimately it's physics. And if you want the answer, you can find it. And I spend an awful lot of time looking for answers because that's what I enjoy doing. I don't have an explanation for why that is, but it's an education that is a bit of an obsession, meaning I'm constantly learning. That's what I enjoy doing.
Okay. I'll just go off on a little bit of a tangent here because we've got a lot of listeners that are following this podcast who are younger, will still be in school, looking to move into universities or college. You mentioned there of the mechanical engineering background, even if you didn't finish that. That and your mention about physics, which is obviously so critical to just about every element of how the car operates. Would you say that those are essential or at least desirable for people going through school and college at the moment to sort of embrace if they want to pursue a career in any sort of element of the automotive industry?
I would say it depends on what level of success they want to have. I mean, ultimately, when you say physics, people think of books full of formula and things like that are hard to understand. In reality, physics is a study of the world around you. It's literally just a method of understanding the world, right? It's sort of like saying these are the tools to understand reality. It's far less complex than people would make it sound. I would say that it is important, really, really important, especially if you're involved in racing, because if you make a change that makes the car better or worse and you don't know why, then what have you accomplished? You've possibly made things better in that moment. Then you move on to the next application, the next race series, the next car. And the only thing that you know to do is what you've done in the past, which may not apply. If you know why those things happened, you're prepared to take on new challenges. And I will say that I don't regret not finishing school because the information is out there. More so these days than when I was a kid. I used to spend a lot of time in the library, the science and engineering library, because there's, wonderful books there. But the number of things that you can learn on YouTube these days is just staggering. It doesn't matter what it is, if it's chemistry or physics or advanced mathematics or your channel. I mean, there's real information out there and you have to sort through it, but it's out there and it's often presented by people who do a better job than some of your instructors might have. We've all had good instructors in school, but there are some people with a tremendous knack for this that put out amazing content. And I predict that a lot of education results from that in the future, as opposed to our universities, which are controlled in many ways by people who are interested in things other than making people understand, right? I'll just put it that way.
Makes a lot of sense.
There's a lot out there, and anything you want to learn, not anything, almost anything you want to learn is on the internet, or at least a guide to learning those things.
Yes, there's never been more availability of information. To come back to your point there, I mean, it is important to be able to sort the fact from the fiction, because just because someone can create a YouTube channel does not necessarily mean that everything they're putting out is gospel. So that's obviously the next challenge that comes along. Coming back a little bit to one of the other comments you made about making a change and maybe the car goes better and you don't really know why. I see that so often, and the other element that goes hand in hand with that is, which we quite often do through necessity as much as anything, is making 6 changes at the same time. And maybe the car goes better. So did all 6 improve the situation? Did 3 of them make it better? 2 of them make it worse, and 1 make no change? And I think one of the things that I took away from university, and I don't always practice it, sometimes necessity means we have to make a bunch of changes and use our seat of the pants or gut feel, but sort of scientific method of coming up with a hypothesis, then forming an experiment, actually going through that experiment and then analyzing the results. And generally, coming back to what I was saying there, making a single change at a time is the way of actually assessing the effect of that change. So many people don't do that. So just wanted to mention that you came up with it, and I think that's really important to know.
There's a part of that that's very important, which is to test things one at a time is very time consuming. Right? To throw 6 things at it at once is expedient. And if you understand what you're doing, often that can get you there quickly. So it's a matter of short-term versus long-term gain. So let's just say that you're a tuner or a calibrator and a new vehicle comes in, something you haven't seen before. You can get after it and get that tune done, make the power, get what you think is reasonable drivability, and get the car out the door and continue to do that and make progress over time, but maybe end up with a mediocre end result. On the other hand, you could spend a week or 2 weeks on the dyno with that vehicle and prepare yourself for the future by doing more carefully detailed tests. In the long run, the quality of the work that you're doing will be far better if you spend that time. Now, it's easier said than done. You have to make a buck, right? So maybe you can't shut your shop down for 2 weeks. But the point is that many of the problems in our industry, I think, are the result of people rushing through those processes.
Yeah, I think you did right. Just on that exact note, with a new car coming out, I think as well, if we look at how complex modern cars are, particularly if we're reflashing the factory engine management system or factory controller, in comparison to what we had off the showroom floor 15 or 20 years ago, the learning curve is much, much higher than it used to be. And I think that favors the shops that are going to get in a new model and be able to specialize in that one model. And they know that they can invest a month of continuous dyno work on that car to really understand it inside and out, because from then on, they're going to be seeing 10 of those cars a week or 10 a month or whatever it may be come through the door for the next 5 years. So it's a little bit more difficult for those shop owners that don't have that niche and have to be able to do just about any model that comes through the door. I digress a little bit though. Get us back on track here. So let's sort of fast forward your career. You've sort of said you got out of the plastics molding, got a little bit more involved in the cars. Where did you go to from there? Like, let's start joining the dots up to the foundation of Injector Dynamics.
Unfortunately, because I like to learn so much, I had a habit of wandering off in many directions at once, and I still do. If I didn't have a business partner, I would probably wander off in way too many directions, way too often. I was involved in doing suspension work and fabrication and engine development all at the same time. I guess you want me to draw a line between that and fuel injectors, basically, right? That's where we're going. So I did a lot of carburetors. I built a lot of carburetors over the years, and built some really unique test equipment to understand carburetors. And then when I moved into fuel injection, I was excited because it should be mathematically determinate. I should be able to say, well, I know what the airflow is at this point. I know the air mass in the cylinder, and I know the flow rate of the injector. So determining the map or the fuel surface should be a simple matter of performing some calculations. And I had a dyno that had both a airflow meter and a fuel flow meter on it, and none of the numbers matched up, and they didn't know why. So it was just driving me crazy to the point of keeping me from getting work done, right? Because I should be able to sit down with my calculator and say, well, this is the pulse width that should result in such and such an air fuel ratio with this fuel. And it didn't.
Let's just come back one step for those who may be a little fresher to this. So, when we're talking about what we're trying to achieve here is to get a specific air-fuel ratio, and that is simply the ratio between the mass of air that's in the cylinder and the mass of fuel that has been delivered via the injector. So what you're saying there is you've got an airflow meter, you physically know the exact mass of air going into the engine, therefore, as it was said, should be easy to get the correct mass of fuel. We know the flow rate of the injector, calculate the pulse width, happy days, and it's not working.
Yeah, that was exactly what happened. I made a lot of phone calls, and the result was either crickets chirping on the other end of the phone or people trying to dissuade me from getting answers to those questions. It was odd, at least in my opinion. So I stole the fuel. Well, I didn't steal the fuel flow meter from the dyno, but I used the fuel flow meter from the dyno along with a test rig that I built up to test the injectors and see what was going on, to try to figure out why none of the numbers matched up. I quickly found that what we thought injectors did and what they actually did were two different things. I spent a lot of time being confused, eventually figured it out through lots of testing. I don't know, somewhere in the middle of that, injector dynamics was born. I think I glossed over a lot. Knowing your audience better than I do, maybe you can dial me back to some specifics that are critical.
No, I mean, I think that's probably a pretty good way of quickly covering off what I can only imagine was maybe 10 or 15 years of your life. Important to mention, you are a tuner, or were a tuner as well, so you're intimately knowledgeable on what these things are doing, and as you say, they're not quite performing the way you think. And I know at the start of my tuning career, there wasn't a lot of knowledge around injectors. There wasn't the understanding of injectors that we now have, and a lot of that I do think is thanks to your work and injector dynamics. We'll talk a little bit more about how that's impacted the rest of the industry as we go through this. But even to the point of ECU manufacturers that I was dealing with at the time, they had no injector dead time table or injector offset, whatever you want to call it. There was no understanding that was an element, and if you don't know what that is, we're going to talk about it in detail, so don't worry. But these are the tools that we had available. Yes, there were higher end products that did understand that, but not to the level we've currently got. And the end results that we're able to provide. I mean, yes, you could tune an engine, and probably even if you had no dead time compensation in the ECU, under wide open throttle, it'd be there or thereabouts. If your ratio might move around a little bit, but where it really became apparent was particularly at idle, your idle quality and your compensations wouldn't work. And I mean, I know I scratched my head probably much like you were, and thought, well, why isn't this working like it should? There's got to be something missing.
It's a machine. It ultimately should respond to logic, and it wasn't. Well, actually, it was. It's just that we had all the wrong assumptions, essentially.
Yeah, sure. Before we get into more of the specifics around injectors and characterization, let's talk about the options. And if I'm talking here back around that sort of 15 to 20 years back from now, what we had available in terms of fuel injectors if we had an engine we were tuning and we knew that we were going to exceed the capability of the factory injector. We needed a way of getting more fuel into it. What were the typical sort of go-to options there?
Almost all of the options were very old injectors. The old, what I call the Bosch EV1 style. You remember the steel body? It was about the same diameter as a U.S. quarter. Let's see, how many, 25 millimeters. Sorry, I got to remember where I'm at, where you're at. Most of them required a peak and hold drive circuit. And there were newer injectors that were available that typically flowed less, sometimes considerably less. And those hadn't really become common in the aftermarket. It was the old style injectors that were still what was being used. And the response of those injectors was just absolutely horrible. I mean, they were fine for their time, but I mean, we're talking about injectors from the 70s and 80s, and it's 2004, and we're trying to use those injectors when there's much better stuff on the market. And how I arrived at some of the newer technology was Motec started sending me customers to characterize their injectors so that we had the correct data to use in the ECU, so that the mathematics in the ECU would function correctly. And I'd get all different things, and I would quantify the response, and I found that the newer injectors were indeed far, far better. And so then it turned into a search for the highest flowing of the new injectors. And then it turned into modifying those injectors to increase the flow rate. And then most importantly, being able to quantify the effects of those modifications. Um, but I think I got a bit off track. The short story is, what were we using? Old EV1 injectors was kind of the common thing. Old Rochester peak and hold injectors, which were maybe the worst thing on the planet. Not quite as bad as cancer, but almost. They're pretty awful. They're really bad. Yeah.
Yeah, fortunately, if you're only involved in drag racing, the idle quality and the drivability don't really matter too much. And these injectors, while they are horrible things, they kind of did actually get the fuel into the engine, which was what we really cared about. But, you know, I've always said that it's much harder to get perfect drivability, great cold start, and idle quality in a modified road car than it is to tune a drag engine at wide open throttle, even if it's making 1,500, 2,000 horsepower. So there's subtleties here that affect different styles of engine operation differently. Now, there's a couple of terms you use that I want to dive into here. So peak and hold. So that's a style of injector which also needs to be matched with the correct injector driver in your ECU. And then the EV14 or the more modern injectors are now all saturated drive, which is much easier for the ECU to actually function. So we don't have the benefit here of nice graphs, which makes this discussion a bit easier. But could you give us a real quick overview of peak and hold versus saturated drive, why peak and hold existed and why it's a thing of the past?
I'll start with why it existed, and that is that a fuel injector is nothing more than a mechanical valve, which is controlled with electricity. It's a solenoid attached to a valve. And the mass of the early components was very high. So in the same way that it takes a lot of horsepower to accelerate a heavy car, it takes a lot of power to accelerate a high mass valve, right? And so the coil, which is what forms the electromagnet, which pulls the valve open, had to generate a tremendous amount of force. And so it was a very low resistance. And if you remember Ohm's law, the lower the resistance, the greater the current flow for a given voltage. And so that was required to generate the force to pull the valve open. The problem is that once you got the valve fully opened, the current requirements were very, very low. And if you maintained high current flow during the injector open period, you were doing nothing but generating heat, and a lot of heat. And so the way a peak and hold system worked is that for a prescribed period of time, it would apply full battery voltage to this low resistance coil or low impedance coil to generate a lot of force. Once the valve snapped all the way open, it would go into a mode called pulse width modulation, where it would cycle the injector or cycle the coil at a very high frequency so that it may only be receiving 25 to 30% of the current that it was initially. So the heat was quite a bit less. And the frequency of cycling on and off was so high that the valve itself couldn't respond.
Essentially, we need a high peak current to quickly open the injector, but once the injector's open, it doesn't actually need that amount of energy, so the holding current is much lower, and therefore we don't get the heat. So, I mean, joining the dots here, one could assume that the modern crop of saturated drive injectors, where there are a higher impedance coil, typically what sort of 9 to 13 ohm impedance if we measure it, there or thereabouts, the internal mechanism, the valve, etc., everything that's inside the injector is much lighter, hence it's easier to actually get it open quick. Is that kind of a good summary there?
Yeah, and going from memory, which is vague, by the way, I haven't thought about these details in probably a decade. You know, the development period involved this stuff being all fresh in my mind, and I've been focused on so many other things since then that I'm not going to say I've forgotten the basics of how an injector works, but I'm having to dig deep, and I'm probably less articulate on the subject than I used to be. But in any case, from memory, I think you'll find that the valve itself in a modern injector is approximately 1/10 the mass of the old peak and hold injectors. And I did a seminar one year at PRI, I don't know, 15 years ago, where I had a number of injectors disassembled and just passed them around the crowd, and people could see it and pick it up and hold it. And everyone was quite surprised at the difference in mass between the old style and the new style injectors. But essentially, that's what it's come down to: lower mass, lower valve mass.
Yeah, and I just want to come back as well. I mentioned the different drivers inside of the ECU, and it is important, although these days you're almost certainly going to be using a high impedance saturated drive style of injector. I can't even remember the last time I saw a peak and hold injector, but it is important just to understand that, because if you try running a peak and hold injector with a saturated drive without an external ballast resistor pack, that's not going to end too well, is it?
No, and in fact, the practice of using the external ballast resistor was pretty awful as well. Uh, but I'm not going to go into that because hopefully nobody's doing it. And if they
Mm,
are doing it or are thinking about doing it, just don't.
yeah.
I mean, we can go into detail if you want.
I don't think there's any need, because times have moved on, and as I say, I mean, I haven't seen a peak and hold injector now for probably the better part of a decade. So I just wanted to mention it because it's important to understand they do exist, but we'll move on. Now, one of the problems with these newer style of injectors, and obviously things have changed since they first got introduced because power levels have continued to climb even in OE applications, is, as you sort of mentioned, that they weren't really that big at the time. But there
Yeah.
were these techniques such as decapping the injectors, modifying them to increase the flow, that a lot of people were doing both in their home workshops, maybe not the best, but also some of the aftermarket injector suppliers were doing it. So give us the overview. What does decapping do? Are the pros and other cons?
Well, to be clear, we were doing that ourselves at the beginning. And I'd like to make the point that the reason we were comfortable doing that is that we had developed equipment that allowed us to fully quantify the results of that, right? So we weren't just shooting in the dark. And I will tell you that the engineers at Bosch were horrified when they saw what we were doing. But when we showed them the amount of effort and detail that we put into it, they became far more comfortable with it. They still didn't like it, but that got us here. In any case, almost all injectors these days have a plate on the end of them that directs the fuel, typically to two separate intake valves, sometimes to a single valve. But the spray is targeted very specifically, mostly for the purpose of cold start emissions. And so, in having that plate on the end of the injector, on the very end of the valve, not only does it direct the flow, but it does restrict the flow a considerable amount. So, quite simply, if you knock that off the end of the injector, it's not at all uncommon for the flow rate to double. And
Okay.
so, that was the easy way to get high flow.
Yeah, so you're taking a production injector and then actually making it useful for our purposes in the aftermarket where we need a lot of fuel flow.
Yes, and I'll tell you that when we were doing that, our average scrap rate was about 10%. In other words, in the process of doing that, we destroyed approximately 10% of all the injectors. And when I say destroyed, I don't mean they didn't work anymore. I mean their characteristics changed to the point that we could no longer get them to fit consistently into a batch with other injectors or to fit within our window of specified flow rates and offsets. So we were often asked early on why the injectors were so expensive. Well, part of the reason is that we literally threw 10% of them away.
Okay, so I'll imagine that it's a safe bet here that a lot of other people that are selling these same decapped injectors in the aftermarket at the time weren't going to this length. So it's likely you could get a batch and find, you probably wouldn't even know, but have one injector that's either way up or way down on flow, causing some really odd tunability issues.
Yeah, quite possibly. I mean, there was a time when we measured some of those things when we'd look and see what was going on in the market, but I think we moved past that. But yeah, absolutely. If you modify the fuel injector, it's hard to know exactly what the end result is going to be. I mean, in terms of manufacturing tolerances, I think it's safe to say that the fuel injector is the most precise device on a modern car. When I say precise, I mean the valve lift is measured in microns, right? It's not measured in tenths of an inch or thousandths of an inch, or I'm sorry, millimeters in your
Yeah,
case.
thank you. Appreciate that.
Unfortunately, I grew up here with these awful units that we use, while the rest of the world is sensibly using the metric system.
Yeah, I do try and interchange, but I must admit I do struggle with Imperial a little bit.
It's awful.
Okay, so let's move into injector characterization, which is a term that gets thrown around quite a lot, and I think probably for the most part without a lot of real understanding on what it means. And give us your take. What does injector characterization mean to ID?
The difference between what an injector does on a running engine and what it does when it's held wide open on a test bench are two entirely different things. And when we first came into the industry, the majority, or maybe all of the testing in the aftermarket, was just apply voltage to the injector, hold it open into a beaker, and see how much it flows. Unfortunately, we literally never experienced that in a vehicle, right? It's always being cycled dynamically, and hence the name injector dynamics. That was my way of specifying what it was we were doing that was different. And so on any modern engine, the injector is firing every 720 degrees, and it may be open for 2 milliseconds, 12 milliseconds, 7.435 milliseconds, right? And we need to know when the injector is being cycled on and off dynamically, how does it respond? And we start to run into issues with, or I shouldn't say issues, but we find that at high duty cycles, sometimes the response of the injector changes and becomes nonlinear because the injector does not have time to close fully and for the coil to discharge fully. We end up with a situation at very low pulse widths where the valve is not open fully before it's released, and so we end up with a nonlinearity there. We also end up with a nonlinearity in the area of coil saturation. So for a given voltage and resistance and coil inductance, which is the mechanical equivalent of that would be inertia, the coil doesn't saturate fully until, on most of our injectors, about 2.5 milliseconds. And so what happens is that changes the amount of time that it takes to discharge. And when you hit it with voltage again, the response is different. So we end up with a nonlinearity at the lower end of the range and at the higher end of the range. And then also in terms of dynamics, we find that the injector doesn't always close the way we think it will due to fuel rail pulsations. And so I think I kind of murdered that. I probably should have let you describe that. You would have done a much better job.
Well, let's just sort of take a real simple view, because there's a lot of complexities around this. Unfortunately, isn't a simple thing. But what you started by saying there is we originally bought an injector, or was given an injector that we were told it was 1,000 cc's per minute, and that might have been at 3 bar of fuel pressure. And as you say, with the injector just held wide open at 100% duty cycle.
Right.
So the problem with that is 1,000 cc's at 100% duty cycle, we may assume that therefore at 50% duty cycle, well, what's it going to be? Half of that, 500 cc's per minute. But it's not that simple, is it? That's where all of these complexities come in here. And I mean, again, we don't have the benefit of nice drawings in a podcast. We'll try and link a couple into the show notes for people who want to go a bit deeper. But I mean, if you actually look at the full range of injector flow, it should be a straight line, but it's not. We've got these non-linearities, particularly at low injector pulse widths, and then, as you mentioned, non-linearities again at the very top. In the middle, it does do a pretty good job of approximating a straight line, though, doesn't it?
Yes, it absolutely should. Yeah, that's what we describe as the linear operating range of the injector. The important thing to note about the linear operating range, though, is that there is an offset there, which I call injector offset. You might call it injector latency, injector dead time, whatever the case may be. And the reason for
battery
that,
compensation is another one that I think Motec use.
Yeah, and the difference between that and holding an injector wide open is that every time we tag that injector with voltage from the ECU, it takes some amount of time to respond because it is a mechanical device.
Yeah, so this is the bit that I think a lot of people new to fuel injection and tuning completely ignore. They think the ECU signals that injector to turn on, bang, it's open, it's flowing fuel. And again, just as easy to forget is when the ECU no longer wants the injector open, bang, it's closed, the injector stops flowing fuel. But that's not the reality. Because of this inertia, you've got this mechanical device that physically has to be opened against the fuel pressure as well, and then it has to be closed. So, what's the easiest explanation of that term, dead time, offset, latency, whatever you want to call it?
Well, I call it offset because mathematically that's what it is. But let's bring it back to something that makes sense to guys tuning cars. The end result of that is that the dynamic flow of the injector is considerably less than the static flow rate of the injector would suggest, right? In other words, we're wasting time. We say, hey, turn on, and it says, okay, I'll get around to it. And then it finally does, right? And so let's just say you have a vehicle where the injector pulse width is, let's say, 10 milliseconds. That's the amount of time that the ECU is energizing the coil. You may get only 9 milliseconds worth of fuel. And so the key to that is knowing that the dynamic flow is less than the static flow, and that's where people get into trouble.
Okay. From a tuning perspective, how does this offset, dead time, whatever we want to call it, how does this actually impact on the results we're getting with our calibration? And by this, I'm saying, let's assume our dead time, we're either not factoring that in at all, or our dead time values are completely incorrect based on what the injector is actually doing.
It results in substantial nonlinearities. Now, even in the linear operating range, and here's why. If we have an injector that flows 1,000 cc's per minute, we should be able to draw a graph and draw a straight line from that flow point down to zero and say, well, this is what the injector flows. If I keep it open for a half a minute, it flows this many cc's, right? Well, that's obviously not the case because we have that approximately, let's just say 1 millisecond delay for the sake of conversation. Now, here's where the problem arises. At a 10 millisecond pulse width, you're only getting about 90% of the fuel that you think you should be getting. With a 2 millisecond pulse width, you're only getting about half of the fuel that you think should be getting because 1 millisecond is a much greater portion of the total pulse width. So that creates a substantial nonlinearity where the errors due to incorrect injector offset being programmed into your ECU have a greater effect at low pulse width than at high pulse width. And ultimately, the flow of the injector ends up not being proportional to the pulse width. And so let's say you're racing at Pikes Peak and you got to climb the mountain and you're going to lose air density and you need to lean the engine out by 20, 30%. I don't know what the numbers are. I should know. The ECU needs to pull the fuel flow back by 20 to 30%. But if the injector flow is not proportional to the pulse width being delivered to the injector, then that doesn't happen. You may lean it out 40% or 10%. It's either going to go rich or it's going to go lean. And so by including that offset value, by telling the ECU, hey, you need to apply voltage for an additional 1 millisecond, now the fuel flow becomes proportional to what Motec calls the effective pulse width, but it's not proportional to the actual pulse width. And the end result from a tuner's perspective is simply this. When you tell the ECU, make the engine richer by 10% at this point in the operating range, if your injector offsets are correct, that's what you get. If they're not correct, it may be 5%, it may be 17%. That's really the issue. That's where it comes into play. And it gets particularly problematic when you consider that injector offset is a function of both fuel pressure and battery voltage. Now you have a lot of variables there that need to be accounted for in the ECU.
Yeah, let's just come back and dive into this a little bit further, because one of the arguments I've heard tuners give me is, well, it doesn't matter if my injector offset's not quite right because I'll just change the numbers in the fuel table. And okay, yeah, sure, to a degree, that is going to get you the air fuel ratio at that particular point that you're after. The bit that's easy to overlook, though, and this is the stuff that sort of the ECU is doing in the background, it's constantly running compensations for varying intake air temperature, just as one element. So it's got a air temperature compensation table, and it knows as the air density changes, this is what I need to do to the fuel being delivered to maintain a consistent air fuel ratio. But it's applying those corrections on the incorrect assumption of what the injector flow is going to be. So that's the bit that's easy to overlook, is none of your corrections are going to actually work as you'd expect it. So when you get all of this stuff spot on, and there's a bit more that we'll talk about in terms of other aspects as well, all of a sudden the ECU is able to do its job properly. From our perspective as tuners, it just becomes easy. We don't have any weirdness going on, and it just all works. So I think I wanted to get that in there because a lot of people just don't think that this stuff is as important as it is.
Yeah, and it becomes important very quickly. Of course, if you're racing at Pikes Peak, like I said, but you bring up a better point, which is air temperature. So let's say the vehicle is turbocharged. Air temperature is all over the place, as we know. Inlet air temperature goes up, so the fuel mass in the cylinder goes down. The ECU says, I have to lean it out 10%. If your battery compensation values are incorrect, it might just lean it out 5%, in which case you're rich and safe and you make less power. Or it might lean it out 15%, in which case you run lean and put a hole in the piston. So these compensations have more to do with maintaining a consistent tune than they do with what you're able to accomplish there on the dyno or strictly battery voltage, whatever the case may be. And there are people who will do a calibration and turn off all the compensations. And well, they're going to blow things up, and they do. You see it all the time.
Mm. And I think on a tangent here, I think another thing that has probably got a lot of tuners through by the skin of their teeth is that closed loop fuel control now on a lot of platforms is so
Yes,
good that it can almost mask stuffing up the basics or doing a poor job of the fuel calibration in the first place. So I think a lot of people are leaning too heavily on that. But the problem with that is what happens when your sensor dies and all of a sudden you're back to your base map with no closed loop comp. And then you actually see the ugliness that
sure.
really is in there.
And another thing that makes that easy is drag racing, in the sense that you can abuse a motor for 6 or 10 seconds at a time and potentially get a very different result than abusing a motor for 30 seconds at full throttle down the straight, running around a road course, that type of thing. So drag racing definitely makes it easier, as do alcohol fuels.
I mean, I think the other thing which you've already mentioned there as well with drag racing, you kind of really always operating at that high RPM wide open throttle area. So the injector pulse width, if your dead time's wrong, you're in that situation where your injector pulse width relative to the dead time is so big that errors become a little less critical. I think the worst case scenario is actually a road driven car, because at idle and light throttle cruise, that's the area where your dead time is actually making up a more significant portion of the overall injector pulse width. Hence, errors there become magnified. So, yeah, very difficult to it's not apples with apples. And drag racing is such a unique form of motorsport that it almost doesn't sort of come into this conversation. All right, so we've talked about the injector dead time, offset, whatever we want to call it. And, as cars have become more complex and the factory engine management controllers have also become more complex, these OEs have gone a step further in terms of more thoroughly characterizing the injectors. And GM and Ford, for example, GM uses a short pulse width adder table. Ford go about it a slightly different way with their high slope and low slope characterization. What do those terms mean, and why do they need that information?
Both of them exist, obviously, to ensure that the fuel mass being delivered is correct, even when the injector is running in the nonlinear operating range. And essentially, what Ford did is simplify that. So you could argue that the way GM does it, by generating a table that says, for this pulse width, this is the correction; for this pulse width, this is the correction. Ford has simplified it. You could argue that GM's method is better. In practice, we find that the Ford method works relatively well, because stock injectors in stock applications tend to not run in the nonlinear range very often. But ultimately, there are two ways of describing the same thing. And if we had a graph to show, I could show you how there is an inflection point between the linear and the nonlinear operating range. And for a high quality injector, the what Ford calls the high slope area, which is the linear range, is a straight line. And the nonlinear portion can pretty well be approximated by a straight line. It works better than you might think. In any case, the point is, when the injector gets in that range, if it's not accounted for in the calibration, the problem is just as bad as having incorrect injector offset. So that's critical to making any of these work. And of course, when we put bigger injectors in these vehicles, it becomes even more critical, because we often operate in the nonlinear operating range with a large injector.
Just to try and maybe simplify this down a lot, because it is, again, without pictures, it's a lot to sort of try and explain. But I mean, essentially, as far as the ECU is concerned, it's just considering that the injector flow right through its entire range is linear. So if we double the injector pulse width, we're going to get double the flow coming out. It's compensating for the offset. We already know that. And these two techniques, either the Ford high slope and low slope or the GM short pulse width adder, are basically just giving the ECU tools to get the actual flow to that linear approximation that the ECU is using, so that every calculation that the ECU does actually results in the mass of fuel being delivered through the injector that it's expecting. Is that a good way of breaking it down?
Yes, it's describing the characteristics of the injector throughout its entire operating range, so that any nonlinearities are accounted for. And if it's done perfectly, then the end result should be perfect. Of course, we know in the real world that's not the case. That's why we have closed loop trim. But essentially, it's just saying, under every operating condition, this is what you can expect of this injector. And again, when we put big injectors in a car, it becomes more critical because we get into those areas where the injector is operating in a nonlinear manner.
Yeah, I'm guessing there's probably a few people listening at this point who are thinking, yeah, cool, so why does all this stuff matter? And I mean, if we're looking at the OE world, it really matters because obviously they need to meet emissions standards. So being able to very, very accurately control the air-fuel ratio, it becomes much more important for them. However, where it really comes into its own, and anyone who's done a lot of OE tuning will have been in this situation, you get a GM, LS, whatever it might be, and you want to put a blower on it, and obviously that requires a bigger set of injectors. So in the older days with an aftermarket ECU, if you made an injector change, often it would require almost a complete remap of the fueling because you're manually baking in these errors or fixing these errors inside of the fuel table. Now with these modern controllers from the likes of GM, you go through, you put your bigger injectors in, your ID1000s or whatever they may be, provided you've got the right data, which we'll get into. It's simply a copy and paste of all of that data into the relevant tables, flash that into the ECU, lo and behold, start the car, and it runs exactly like it did on the factory injectors. I mean, the first time I did that, I was looking at this thinking, this is some voodoo shit going on here.
And when in fact, it's just really simple mathematics. Yeah. Amazing, huh? I mean, I do that here all the time, especially with the UTVs that we're working with a lot now. They're very popular here in the US. And we do it all the time. We change injectors. We put, pump out gasoline, put methanol in it, put ethanol in it, change injectors, change fuel pressure, copy and paste the data in and get in it and drive it. If you log the oxygen sensors at that point, you can say, oh, look, there's a 4% error here and it's 2% lean here. And, it's not exact because nothing in engine calibration is exact. But if I were to just make that change to one of my vehicles, whether it's one of my muscle cars or UTV or whatever is here, if you got in the vehicle and drove it, you wouldn't know that anything had been changed. I have a ZL1 Camaro that I used to run at the track. It doesn't have an oxygen sensor on it, other than the factory narrowband sensors for closed loop control at idle and cruise. I switched that over to E98, put 1300s in it, copied and pasted the data in the ECU, and I took it to the racetrack that way for an entire season. I never monitored anything. I just assumed that the air fuel ratios were correct. I haven't blown it up, and it runs great. Drivability is excellent. Cold starts are good. Hot starts are good. So I'm sure if I monitored it, I could say, oh, there's an error here, there's an error there. But
you're well within the ballpark, though, clearly.
I just never even checked. I mean, I ran on the track that way for the better part of a season without issue. So
you can't argue with the math.
Well, I mean, it's kind of cheesy. We call it plug and play. That's what we started calling the stuff way back when. We sort of stole that term from the computer industry. But if it's right, it truly is plug and play. Put the data in, hit the key, and drive the car.
This sort of begs the question, though, and it is going to be a case of garbage in, garbage out. So it all relies on this data being correct.
Yes.
So I'm interested, can you sort of talk us through how you are generating this data at this sort of level?
It's less complex than you might think. It's mostly a matter of paying attention to fundamentals. So injectors come in from Bosch. They get unboxed, serial numbered, put into a machine that runs them at, I'm going from memory, I hope I don't screw this up, runs them at the equivalent of 12,000 RPM for a half an hour. Because every mechanical device undergoes a break-in period, right? So the first thing we do is break them in.
Right.
From there, they go on the test bench, and what the test bench does is cycle the injector dynamically throughout its operating range. The entire time that it's doing this, it's simply measuring flow through the injector, and it generates a data set in the form of a graph and raw data. Based on that raw data, we perform some relatively simple mathematics that describe the flow rate of the injector and the nonlinear range, and then we match the injectors based on their response through both ranges. In fact, that's something somewhat new for us, which is called the dual slope matching method. We match it based on both the linear and nonlinear operating range. So it's literally just a matter of measuring the injector characteristics, defining them mathematically, and then matching the injectors as a result of that. And I don't know if that's more or less info than you wanted, but
There's a couple more bits that I want to dive into, but dynamically matching the injectors like this. So safe to assume that the reason you're doing this is because if you bought 1,000 injectors from Bosch and you ran them all through the same test, there is a variation across that 1,000
Yes.
injectors. So
Yes.
therefore, you are trying to match these so that when a person buys 4 or 8 or 20 injectors from you, those are within a match set. So the variation across that set of injectors is minimal.
Yeah, not just match within a set, but they have to match a specific flow rate plus or minus 2.5%. And the reason for that is that a decent percentage of our sales goes to manufacturers who are putting them in kits, right? And I mean, there's all different groups of customers doing this, but one example that just popped into my head is here in the States, Dodge SRT created 1,000 horsepower crate engine. Did you ever hear about that? They call it the Elephant. I don't know
Yeah.
why, some historical reason. But the point is that thing comes with ID 1050s in it. You can buy it from Dodge, 1,000 horsepower, 426 cubic inch Hemi. And like any production engine, they don't test every single one on the dyno and do a calibration on that particular engine. So they need consistency in the results. And so, in addition to having matched sets, we have to say, hey, these fit within a plus or minus 2.5% window. There are supercharger kits. I mean, it's a long list of manufacturers that are using these injectors, and they need to fit within a pretty tight flow range so that the end result ends up being good. I mean, they can't blow up every 17th engine that leaves the factory because it's running lean.
Yeah, that's not going to be ideal.
Yeah, and it's a pretty detailed process. I mean, again, breaking them in before testing them because the characteristics do change somewhat, matching them within the linear and nonlinear operating range. It's fairly extensive, but the end result speaks for itself in the sense that numerous manufacturers, including automotive manufacturers themselves, are able to rely on them and put the product out on the market and not be afraid that customers are going to beat their door down because an injector was out of spec.
I'm interested across a decent sample size of injectors. I said 1,000 before, but whatever that might be, what sort of variation do you actually see across what should be essentially the same injector from Bosch? And is there a portion of the injectors that you buy that you actually have to
Yes.
essentially trash?
Yes. So when we were modifying injectors, on average, we were about 10%
Yeah,
waste.
yeah,
Currently, now that we no longer modify them, now that everything is built by Bosch to our spec, our waste on average is about 2%. And I say waste, it doesn't mean the injector's not good. It means it doesn't fit within the operating range that we specify. And we do tend to use those for, customer projects, or I'm sorry, employee projects. Maybe a customer, maybe a guy like you says, hey, I'm doing something for my race car. Do you have something kicking around? I'll say, here, take these. It's a fully matched set, but they flow 3% more than nominal or 4% less than nominal. It's a good quality set. But yes, the average waste is about 2%. And in terms of spread, I don't know how interested you are in statistics, but when we plot the flow versus quantity of injectors, we find that it follows a Gaussian distribution, as almost all machined devices do. And so Bosch will specify plus or minus 5% at 3 standard deviations, for instance, for a production vehicle. Ours ends up being a little tighter than that because people are being so abusive, right? I mean, a production vehicle has large safety factors built in.
yeah,
And
definitely.
well, you guys don't really work much on safety factors. You just want to go like hell. So they've got to be matched pretty tight.
It's a lack of safety factor.
Yeah, so the consistency that we get from Bosch is absolutely staggering, but still it doesn't quite fit into the range that we specify. So I think if I work that out for those interested in statistics, I think our 3 sigma point for what we put out the door, I think it's 2.5%. Yeah, I think that's where we end up, and it's about 5% for a production vehicle, which is relatively standard.
Sure. All right. How, going a little deeper, how are you actually testing the injectors? Is this production injector flow bench equipment, or have you had to go and invent your own technology here to get the data at the level you need it?
Yeah, we definitely did. So going back to the beginning of this, when you asked how I got here, and I said, well, I built a little rig to measure the flow of the injectors. That just about drove me crazy. And for the longest time, I didn't understand why. And as it turns out, there were numerous issues related to density and viscosity of the fuel changing. And the flow meter that I was trying to use at the time ended up, as it turns out, being very sensitive to both viscosity and density. Pulsations in the fuel rail would skew things often and make the linear portion of the injector flow range look nonlinear. It was pretty ugly. I would say the biggest challenge that I faced in building injector dynamics was in building test equipment to properly characterize the injectors. That was absolutely the hardest part. It's easier to get bad data than it is to get good data, which is probably true in everything you're doing in automotive. But getting bad data is easy. You've probably seen videos of one of the injector test benches. I call it the piss in a bucket method. It's got the graduated cylinder with the injectors up above,
Mm.
and if you see one of those cycling, sometimes you'll see the pressure gauge on the end of the rail bouncing back and forth, 20, 30 psi. That will absolutely destroy any semblance of accuracy that you might have had.
I'm glad that you raised that particular point. You sort of get this, I don't know, we liken this to sort of a water hammer effect when you've got fuel flowing into the rail and then you've got the injector opening and closing. So
Yes.
this is causing these pulsations that you
Yes.
mentioned there you're seeing on the pressure gauge. So from what I understand, and again, I've talked to you about this years and years ago as well, you went to a lot of trouble to build a test rig that actually eliminated that and held, or at least I guess as close as you can, a consistent pressure for the injector for this flow, correct?
Yeah, deviations in pressure that are low enough that they don't affect the end result. So, in other words, you can continue to improve the test bench to the point where further improvements in making the fuel pressure steady no longer affect the results, right? So, I only bring that up because I can't say it's perfect, and I shouldn't say it's perfect. I mean, nothing is. It's a simple matter of reducing those pulsations to the point where further reduction in pulsation no longer has an effect on the output. And that's the one thing of every question you're going to ask me. That's the one thing that I won't tell you how I accomplished.
Absolutely. It sounds like there's a lot of development went into that. And yeah, we don't want to try and get you to share all of your secrets. My question from this, though, is that the manufacturer of the car that we're fitting your injector dynamics injectors into probably hasn't gone to that level of trouble in maintaining a consistent fuel pressure. I mean, we set our fuel pressure at 3 bar or whatever it happens to be. And even if we're monitoring the fuel pressure, most people would be logging this at maybe 20 or 30 hertz or something like that, relatively low frequency. Yeah, if you look at the data, it's pretty smooth. But when you actually start getting a little more granular with this, in most applications, there is still going to be some level of this oscillation in fuel pressure as the injectors open and close. It's a dynamic situation. Everything's constantly changing. My point here is, are you generating data, therefore, in a perfect world, to then go and put it in a very imperfect application, and what's the impact of that on the usefulness of that data?
That's absolutely the case. And I can give you a few examples of how it impacts the usefulness. The first point I want to make, though, is that the manufacturers do invest a great deal of time and effort into reducing pulsations in the fuel system for the same reason that we would want to do that, because the ECUs are model based. They know the air mass. They say, I want this much fuel. The injector has to respond the way they want it to. So yes, we're testing in a perfect world and putting in an imperfect world. The question is, what is the impact of the difference between those two? I don't know how much detail you want me to go into. This is an area that I've been working on quite a bit as of late. Actually, let me just give you an example. UTVs. We have a vehicle here in the US, an off road vehicle called a Honda Talon. It's a 1000cc two-cylinder engine. And the fuel system in the car, even the ECU, the calibration, everything is like 1990s technology. It's very odd in that sense, but it's an off-road vehicle, so there are many niceties they're not concerned with. So we first go to fit injectors into this vehicle, and we find that we can't make them fit, so we design and build a new fuel rail. We put the larger injectors in there. I reverse engineer the factory calibration, perform the calculations to change the injector data in the ECU, and I should be able to go out and drive it and be within a few percent of the stock calibration with my larger injectors, because That's my area of expertise. That's what I do. So we test the vehicle and we find that at full throttle, it's approximately 9% leaner than it was from the factory. And I'm embarrassed to tell you how much time I wasted trying to figure out what I had done wrong. And finally, I decided it had to be fuel rail pulsations. Or
Mm-hmm.
I didn't decide, I theorized. Turns out I was correct. We put some very fast sensors in the fuel rail. When I say very fast, I mean a piezoelectric sensor, and logged it at 100 kilohertz, so we could really see what's going on. And I wish I had some of these graphs to share with you. This was an entire summer's worth of work and digging and understanding, not just for this vehicle, but to gain an overall understanding, much further than things you and I have discussed in the past. The short story is that the average fuel pressure during the injector open period with the larger injectors in it was about 20% less than it had been with the stock injectors. Okay. And so the first thing we find is that even with the stock injectors, the fuel rail pulsations were horrific. There was no effort, or I shouldn't say no, very little effort made by the manufacturer to deal with that problem. And when you look in the calibration, you see that much of the calibration exists to account for fuel rail pulsations. In other words, it changed the fueling so much that they had to account for it in the calibration. Now, when you put a larger injector in any system, whether the manufacturer worked hard to correct that or not, the pulsations worsen approximately in proportion to the change in injector size. So if I measure peak to peak fuel pressure pulsations in any system, and then I double the injector size, unless there's a great deal of damping in the system, you'll find that the magnitude of the pulsations approximately doubles. And this can create numerous drivability issues. It can create rough engine running because what will happen is the amount of fuel that goes in on one cycle is more or less than it was on the last. It gets pretty ugly. And if I could show you some of the data, it would be one of those things where you shake your head and say, I can't believe that's real, or why does this thing even run? And so the answer to your question is yes, we're putting it into an imperfect world. Yes, it does have a lot to do with the end result. And without going into a lot of detail, it's something we're working on for future products.
Okay.
Actually, you know what? Let me bring up another example. Subarus are known for having misfires at idle. And as it turns out, the majority of that problem comes down to fuel rail pulsations.
I was actually going to bring up the Subaru example because
Yes.
they are very well known to have an issue, particularly around, I think it's about 2,800 RPM, 3,000 RPM, and Cobb actually did a really nice article about how they solved this. And again, much like you, not at 100 kilohertz, but they logged that fuel pressure and saw that those pulsations and even the factory system. And interestingly, Subaru actually put a big old dirty Band-Aid on the calibration
Yes.
inside of the ECU to try and work around that, which, I mean, I found laughable. On that note, though, just talking about fuel pressure pulsations, because, and I think we're getting probably a little off topic here, but this is probably pretty valuable information. A lot of factory fuel rails will incorporate some means of pulsation dampening, and that's probably fine. I'm guessing it's well developed for the factory application, but as you mentioned, we go and put a bigger injector in and all bets are off. But more importantly, in the aftermarket, we're pretty well known for throwing the factory fuel rail and damper in the bin and starting from scratch with no dampening at all.
Yes.
So the question here is these factory fuel rail dampers or aftermarket fuel rail dampers. I know Radium Engineering are one company that make these. Are these something we should be looking to incorporate, or is it too complex to use off-the-shelf product in 100 different fuel system applications and expect results to be good?
So one of the things that became clear in our testing is that fuel rail, well, first of all, the manufacturers obviously spend millions on engineering this stuff. The pulsation dampers,
Except Subaru.
well, yeah, and they're not the only example. There's some surprisingly bad stuff that happens on occasion in the OE world. But the aftermarket parts sometimes makes things better. They can on occasion make things worse. The reason for that is that the damper itself is essentially a mass on a spring, which has its own resonant frequency. Sometimes that resonant frequency can align with a firing frequency of an injector and make things worse. The best thing that you can do, and we've talked about this before, the first best thing you can do is use compliant fuel lines in the car everywhere, right? They act as an accumulator to help reduce pulsations. The other thing you can do, and unfortunately no one else can see this, but you see that regulator there on the end of this prototype fuel rail? The best thing you can do is put your fuel pressure on the fuel rail. Get it close, because those pulsations, and this is going to sound a little bit crazy until you do the math and realize that it makes perfect sense. The disturbance created in the rail when the injector opens or closes has to be reacted by something, right? Either all of the fuel in the system from the fuel pump all the way to the injector has to be accelerated to meet the new flow rate, or some compliant portion of the system needs to react to basically fill the void created by the injector trying to pull fuel out of the rail. On any return style system, the regulator itself does a wonderful job of that. Well, it does a good job. How's that? And the way it does that is when the pressure in the rail drops, it responds by closing off the return flow. It works better than you might think it would. The problem is that it's communicated, the disturbance is communicated to the regulator at the speed of sound, and that is at the speed of sound in the liquid in the rail, right? So if your regulator is a foot away or 5 feet away, the regulator often cannot respond in time to properly cover up the pulsation. Now, and again, you're going to have to do the math on this to believe me, because it sounds a little bit out there. On that vehicle, the Honda Talon that I mentioned, we have the regulator on one end of the rail. The injectors are approximately 4 inches apart. So one injector is right next to the regulator. The other injector is about 4 inches away from the regulator. Now, I can see the difference in the response of the regulator to the disturbance caused by the injector. I can see a difference in that response time. So we're talking about 4 inches away as opposed to 1 inch away. And it does a much better job of dealing with a pulsation with the injector near it than the one far away. And this is why the manufacturers have put such effort into damping fuel rail pulsations after converting to deadhead systems, because the regulator's 4, 5, 10, 15 feet away. It essentially, it's too far away to do any good. So use rubber fuel lines. That's the first thing. That's a quick, easy answer. The second is, wherever possible, mount the regulator on the rail. If you can't mount it there, mount it as close to the injectors as you possibly can. That's the best thing you can do for your system without going through an entire design process like the manufacturers do.
One thing I will add there, and this is really completely specific to that Subaru example that I mentioned, but that's a very well-known one, so I think a lot of people resonate with that, is in Subaru's infinite wisdom, they also took the manifold pressure signal for the regulator from just one intake runner right down by the valve. So of course, there's going to be some oscillation in the manifold pressure signal as well. So I think, in line with that, if you've got a manifold pressure referenced regulator, you really want to take that from the plenum in the center, where it's going to get a nice, even and consistent signal. So off track, but worth mentioning. I want to jump into injector sizing as well. I mean, this is probably...
Hey,
you go on.
Can I hit you with one more thing before we finish? Because this came up again on the UTVs, because most of them are odd fire engines. If you look at each bank of a Subaru, it is an odd fire engine. I don't remember the numbers, but that's why they sound the way that they do. And one of the problems with fuel rail pulsations is that on an odd fire engine, the disturbance caused by one injector is not fully dissipated by the time the next injector opens, right? So when you can already guess where I'm going with this, when they're not evenly spaced, injector number 1 will have a different effect on the pressure that injector number 2 sees that injector number 2 will have on injector number 1. What that creates is vast cylinder to cylinder fueling imbalances. And all of these UTVs that have 2-cylinder odd fire engines have a separate fuel table for cylinder number 1 and cylinder number 2 for that reason. And all of them, without exception, have corrections between cylinders of at least 10% in the full throttle range, and sometimes in excess of 20% at the part throttle range. So damping fuel rail pulsations is important. It's even more important in an odd fire engine. And a Subaru, each bank of a Subaru or a V8 is ultimately an odd fire engine. So
yeah, I think it's really good to sort of highlight that there's a complex system, and there's so many interactions between the different elements of it. And I mean, we don't need to understand everything at a microscopic level to be able to tune, but having a comprehension of what is actually going on. Certainly when you see some of these things like you're mentioning here about a 10% fueling differential between two cylinders, that on face value, you're thinking, well, why are they different? These sort of elements explain why that's the case.
Let me give another example. For those who are familiar with UTVs, in 2000, what is this, 2020, I believe, Honda, with that vehicle, the Honda Talon, won the Baja 1000 in their respective class. Are you familiar with the Baja
Yep,
1000? It's a
absolutely.
1,000-mile desert race. Okay. Make a long story short, I did the calibration on that engine, and at full throttle, at redline, which was 9,600 RPM, there was a 20% difference in fueling between the two cylinders. So we're talking full throttle, 9,600 RPM, under boost. The vehicles were turbocharged at the time. 20% difference between cylinders that needed to be corrected.
That is massive.
Just to give you an idea of how bad it can be.
Yeah.
So anyway, sorry for the interruption. I'll let you back on track.
No problem. All right, we'll move on to injector sizing, because I think this is one of the more common areas of confusion and questions that we certainly hear is obviously, what injector should I be fitting to my XYZ engine? I want to make this much power, and that's about the extent of the sort of data points that we normally hear about. And I mean, if you jump online and sort of search injector size calculator, the traditional calculators sort of take into account brake-specific fuel consumption, which most people would not have a clue about. So first of all, you're straight off the bat just using a guesstimate there, number of cylinders, and maybe your power target and something around the stoichiometric fuel ratio of the fuel that you're running. You've gone a different route with this, with your own online calculator. Can you tell us why you decided that needed to be reinvented?
Yeah, the first thing is what you mentioned, the brake-specific fuel consumption. There are two problems with that. One is that, for the most part, nobody knows what it is. So that's a leftover from the old days where people were working on engine dynos with fuel flow meters. They didn't have lambda sensors, they didn't have airflow meters, but they had a fuel flow meter, and so they knew the brake-specific fuel consumption, which is so many pounds per hour per horsepower. Now, the problem with that is that it changes as you change fuel. If you change to an oxygenated fuel, the number is skewed. If you change to ethanol, it's highly skewed. Methanol, it's changed by a factor of 2.5 or so. But here's the other thing. If you do anything to change the efficiency of the engine, that changes. And so what I mean by that is measure the brake-specific fuel consumption of an engine on race gas, and then say, well, we've got to put pump gas in this, so we got to pull 10 degrees of timing out of it. It's going to use the same mass of fuel, but it's going to make less power due to the timing that you pulled out of it. Now your brake-specific fuel consumption number is skewed a considerable amount. So the point is that not only was it a moving target, it was a moving target that nobody could even see. What's that number? Nobody knows. They would say, well, it's about 0.5 for gasoline. So one of the things that I realized over the years doing calibrations and attempting to do them mathematically, that's just how my brain works. I can't just poke it with a stick, right? It has to make sense mathematically. I found that within pretty easily plus or minus 5%, I could estimate the volumetric efficiency of an engine at its torque peak and at its power peak, right? So now we're talking plus or minus 5% instead of, I don't know, 0.45, 0.6, 0.55, right? I can estimate it fairly closely. The one thing that makes it tough is how big is your camshaft, right? And so I'm sure when you use that calculator, you say, well, gee, what do I do? Well, a camshaft of 1 is a stock, purrs like a kitten at idle camshaft, and a 10 is a obnoxious, idles at 2,500 RPM barely. That was the best I could do.
Yeah.
In other words, I had to have some guesswork in there. But the point is that I can estimate airflow plus or minus 5% quite often. And from there, once I know the airflow and the air fuel ratio that you intend to run, which is one of the requirements of that calculator, it's a simple matter from that point to calculate what the injector pulse width should be. And then from there, we crank out the results, not in terms of pulse width, but in terms of duty cycle, right? Because how big should your injector be? Well, punch in the data related to your car, which estimates airflow. You can determine fuel flow requirements fairly accurately. I'll say plus or minus 5, plus or minus 10 at the outside, and plot that as duty cycle versus RPM, because that's really what you're interested in. I mean, if your injector is too big or too small, that's where it shows up in duty cycle. So the reason to, I guess, reinvent that, as you say, is we needed something that actually worked.
Yeah.
And To take it a step further, I don't know if you were around for this, but I did a poll on Facebook, and I basically said to everybody, what fuel was in your vehicle, what injectors, what was your duty cycle, right? And we gathered, I was shocked at the amount of input I got. It was several hundred responses, and I had to sort through some that were obvious BS. And then using some basic statistics, I plotted it out, and it said, well, on average, an engine running on ethanol needs 2 liters per hour per horsepower. Figured out the same thing for methanol, for gasoline, and I gave us some pretty good guidelines there as well. So that's the short story.
So the idea behind it is that it means there's no guesswork here. You don't have to take a punt, use an online calculator, buy a set of injectors, put them in your engine, hit the dyno, and find out that they're actually too small for what you're trying to achieve. It's pretty much a 99.9% you're going to be getting the right set of injectors for your application first time around.
I would say 90%, right? Okay. There is some guesswork there, certainly. But 90% is a lot better than 60 or 50, which is what we had before.
Yeah,
in a lot
absolutely.
of cases. I don't want to say it's perfect, but I will say I've had almost no complaints.
Okay.
Right. In other words, it seems to work well enough that nobody gets in trouble.
I'm sure you'll hear about it if it wasn't working. So there's a few other questions that sort of go around this injector sizing, and some of it I think maybe also made it to like urban tuning legend now. So the first of those is, what should our maximum injector duty cycle be capped at? And I mean, back in the day, I think 85% was kind of the line in the sand that a lot of tuners took. I think with more modern injectors, that sort of pushed quite a lot higher than that.
Yes.
But I haven't really seen a definitive answer for this or even data around why it should be limited. I mean, obviously, we've already talked about the upper nonlinear operating range of the injector, so maybe the injector's not going to quite do what the ECU thinks. But yeah, give us the Paul Yaw answer.
So in the old days, it probably had to do with the possibility of overheating or damaging the injector, maybe the drive circuit. I will tell you, I think I can I'm going to tell you either way. Bosch did some testing with a dry injector, and dry meaning there's no fuel going through there to cool the internals of the coil. And they just beat the living hell out of those things up to whatever duty cycle they wanted, and were not able to hurt the injector, right? That's with no fuel in it. So, by the way, don't do that to your injectors. That was just an internal test. With fuel in there, the fuel keeps the temperature of the coil under control. So it's not a matter of damaging the injector. That may have been the case in 1976. It's not the case now. Certainly not with any of our injectors. You absolutely cannot hurt them by running too high of a duty cycle. The problem is what you mentioned before, which is the upper nonlinear operating range. Now, unfortunately, I can define that exactly mathematically, but it is RPM dependent. And nobody wants to take the time to look that up or do the math. So very roughly, as a rule of thumb, all of our injectors are good up to 95% duty cycle.
Okay.
You go above that, 95, 96%, you're going to get into the upper nonlinear range. Then you run into the same problem that you would if your injector offsets are correct, which is that your ECU tries to make a correction based on atmospheric conditions, inlet temperature, and that correction is not correct. Maybe it goes, if it asks for more fuel, it gets a lot more fuel. It asks for a little less, it gets a lot less. So 95% on all of our injectors is safe. The only thing I will mention is that maybe you see 95% on the dyno and you say everything is fine. Well, if it's the middle of summer and then you race it in the winter, now you've gone beyond that, right? So you have to use some common sense. But the short story is none of our injectors have a problem at 95%.
Yeah.
So not just not an issue. It's something left over from the old days.
Yeah, perfect. That's good to know. I think a lot of people probably still think that they're going to potentially do damage to the injector if they do run them at that sort of duty cycle. So good to sort of put that one to bed. Now, the flip side of this is, when is an injector too big? And are there downsides here? Obviously, at some point, yes, there are going to be downsides. I mean, I seem to recall back when you guys released the ID 2000. I think there was a video of you running a set of 4 on, I think it was maybe a Honda Integra or something, naturally aspirated on
Yeah.
on pump gas, and
Yeah.
it idled, albeit 12.5 to 1 or something. I'm really
Yeah.
stretching my memory back here, but yeah, I guess to put it more specifically, if we can achieve our target air fuel ratio at a small pulse width, like an idle, stoic, or whatever we want to tune to, if we can achieve that, is there any downsides of having an injector that is way bigger than it theoretically needs to be to support the fuel flow required?
There are 2 parts to that. So there's a yes and a no answer, right? One answer is that there's an advantage to having an oversized injector in that you can time the injection period to put most of the fuel into the cylinder during the valve open period. And so what happens then is that the cooling effect of the fuel can be utilized to cool the air in the cylinder as opposed to cooling the intake valve and the intake runner walls and that sort of thing. So you can, in some cases, pick up a couple percent there in VE by doing that.
Mm-hmm.
On the downside, if the injector pulse width is so small that it gets hard to control, then there are obvious issues there. But I think you said that as long as you can control it at idle, everything is okay. Yeah, I think that's a reasonable thing to say. I mean, I'm sorry, I keep going back to this Honda, this 1000cc 2-cylinder Honda. Mine is running on methanol with 1700cc injectors in this 1-liter engine, and everything's fine. However, we went up to the top of the mountain a couple of weeks ago, and I found that I was hitting the minimum pulse width limit, and it was idling quite rich because we're keeping it from going down below that. So yeah, you reach a limit.
Okay.
For sure. But you're probably going to get the best fuel vaporization, which will affect drivability, if the duty cycles are high enough that the fuel gets to spend some time in the runner vaporizing from the hot valve and the rest of the metal around it.
Great. I'm glad that you brought that up, because that was the very next thing that I wanted to move into. And again, I think those who may be sort of newish to tuning, it would make sense to think that we inject the fuel when the intake valve is open, so the fuel goes straight into the cylinder. And which sort of comes back to another element, which is how the fuel is delivered via the injector in terms of how it's atomized. And I mean, I've seen a lot of injector manufacturers make quite a big point about how well or how poorly the fuel is atomized as it leaves the injector. So obviously, if it's going straight into the cylinder, yeah, there's an element of this. However, at least a portion of the time the injector is open, it's almost certainly going to be injecting with the intake valves closed. You've only got a fairly narrow duty cycle that you're going to be able to get away with before the intake valve's closed. And at that point, it's firing fuel against the port wall, the back of the valve, which sounds horrible, but when the engine is actually at operating temperature, all of that's obviously scorching hot, which then means that the fuel will actually vaporize off that hot surface. Then it gets injected as a vapor as opposed to tiny fuel droplets. So I've asked a lot of questions or given a lot of information in there. So what do we need to know about fuel atomization versus vaporization? How does that influence the injector choice? And then should we be injecting open valve or closed valve?
I have spent a lot of time playing with injector atomization in the early days. And there were some times when I could find a little bit here and there, and times when I didn't. More often than not, I didn't find much there in terms of improvement. I guess the first question is, when should we be injecting the fuel? Well, I'm sorry, back to what you said before. The fuel is quite often not being injected during the open valve period. I mean, let's just consider that you're at 80% duty cycle, for instance. Well, the induction period is really only about 180 degrees long, no matter what your cam profile is. I mean, piston from top dead center to bottom dead center is only 180 degrees, right? That's the induction period, more or less, and the flow is quite slow through a considerable part of that. Imagine taking a bottle of glass cleaner and pulling the trigger and noticing all these fine droplets coming out of the tip of that thing. And you think, wow, that's good atomization. That's going to make good power. All these wonderful things are going to happen. Well, now go spray it on the glass and it just runs down the window. Well, the same thing happens in your engine, right? You're not spraying it into the air and saying, look at that perfectly atomized cloud of fuel. You're spraying it up against pieces of metal, in which case it condenses, which ruins all the great atomization that you supposedly are offering. So that's a pretty important consideration.
And
Uh,
just to add to that, I mean, essentially, unless you're capping your injector duty cycle at no more than maybe 25 to 30%,
yeah,
some amount of fuel is inevitably going to end up landing on the back of a closed valve. It has to.
in practice, in most applications, more than half of it. Yeah.
Okay.
So, what are you going to do about that? You can atomize it as well as you want, and then spray it on the runner wall.
So this sort of comes back to another element when we were talking about decapping injectors. You mentioned that sort of diffuser plate, sometimes will be designed by the manufacturer to actually provide essentially two funnels, jets of fuel. I'm not using the right terminology. Targeting that down to the valves. And I mean, obviously, anyone who's seen a multi-valve head, the intake ports have got a nice divider. Generally, the injector is going to be located pointing at that divider. So we throw the factory injector away, put in an aftermarket injector that no longer divides that flow, and it's purely just wetting down that port divider. So that's a concern, I know, for a lot of people, but essentially on the basis of what we've just talked about, makes no difference.
It does make a difference, and the time when it makes the most difference is in cold starts. So the work that the manufacturers put into targeting an open valve has to do with cold starts, and more importantly, emissions during those starts, right? So the injector does a reasonable job of breaking the fuel into small droplets. The smaller the droplets, the easier it is for them to convert from a liquid to a vapor, which means it's going to be easier to get the car fired up. It's going to be easier to pass emissions, right? Because you have less unburned hydrocarbons coming out of the engine. Once the engine is hot, we find that it makes very little difference. In worst case, if you're spraying more fuel on the runner wall than you would otherwise because of improper injector targeting, the biggest difference would show up in transient response, which is tunable in the ECU. So it would be unfair for me to say it doesn't make any difference, right? But I do think it's fair to say that in practice, I don't know that I've had people say to me, man, since I put your injectors in, I just can't get good transient response. And I find that most people don't even change that part of the calibration.
Yeah.
So that's what it comes down to for me. It's not something that it's been less of an issue than I would expect it to be. But to be fair, it does make a difference.
I think why I wanted to raise it is because I know I've heard a lot of people are worried about it. It comes up from time to time. So just wanted to sort of discuss that it's probably less of a consideration than most people think. The transient element, and that sort of gets into a whole different discussion about fuel film and puddling on the port wall, which I think we'll probably park that and leave that for another day. But yeah, essentially, you can tune around that element as long as you understand what's actually happening and what the required inputs are from the tuner.
There are a number of our injectors that are used in emissions compliant applications where they've got to go through and do all the EPA testing, and they're passing certification. So I think it's safe to argue that it would be easier to pass that certification on the cold start with a properly targeted injector. But the fact that they're getting these certifications without specific valve targeting, I think is maybe the best answer to our question, because emissions requirements on cold starts particularly are much harder than anything we have to do in the aftermarket.
So onto injector dynamics. I mean, if you could maybe give us at the moment a sort of a high level view of what the operation is, where you're based, how big's your facility, how many staff, etc.
Well, it's split up into two facilities. There's Texas, where they handle fulfillment and dealer accounts and all of that. And then there's Arizona, where we handle engineering and production. Let's see, here in Arizona, we have somewhere between 20 and 25 employees. I'm not sure exactly how many. We occupy, including the R&D shop. Let me think about this. We've got about 15,000 square feet. We're processing about 15,000 injectors a month.
Wow.
So I know. Yeah, exactly. There are a lot of guys in Texas as well, at least as many as there are here, but probably half of them are committed to the T1 projects, all the race cars that they build. So roughly, I would say injector dynamics requires about 30 people to keep it going.
Okay. And just your mention there of T1 for those who aren't sort of joining the dots here. Tony Palo from T1 is the sort of the retail and marketing side of Injector Dynamics, correct?
If you could call anything that we do marketing, yes. And I'm not being unfair to Tony. Actually, what makes that work so well is that most of our customers are not the end user. Most of our customers are tuners and wholesale establishments. And on the rare occasion that I do talk to them, they're absolutely thrilled with the service that they get from Tony's side of the business, which is shipping things out on time, keeping in touch with customers, treating them fairly. So we don't really do much marketing. We tend to focus on just trying to do a good job. So far, it's worked for us. I just want to make that point that what makes that work over there is competently and fairly dealing with our customer base, not putting ads in magazines and making silly videos to put on the internet. That's. I'm not saying we've never done that, but that's not our thing as much as it is just putting a quality product out there.
Sure. Now, we've already talked briefly about your involvement with Bosch, and at least to the best of my knowledge, you're the only one in the aftermarket industry that has that relationship direct with Bosch. So that's kind of allowed you to separate yourself, I guess, quite dramatically now from competitors in the market, in that you are working with an OE manufacturer.
Yes.
I'm interested, sort of, how does that relationship work? Because at least as I understand it, you're actually still manufacturing some components for these injectors. Is that right?
Some, yes. The short story is that, well, everybody knows what Bosch is capable of. I don't need to go into detail about that. Some of the injectors that Bosch makes for us are able to be built with existing production parts, right? So you've got a company that builds fuel injectors for just about every car on the planet. And there's this valve and this valve seat, and there's this coil, and there's this body. There are all these different parts that make up the injector. And what we've done is go in and pick and choose those parts and those parameters, valve lift, spring force, valve seat angle, that type of thing, to get the product that we want. However, when we got to the 1700, we ran into a problem where we did not have enough magnetic force to pull even that lightweight valve off the seat in the manner that we wanted to. We had to deal with the inertia of the valve, which is quite low, but also the hydraulic force from the fuel trying to hold it shut. And so the answer was to build a new magnetic circuit. Now, because Bosch is such a large company, designing a new magnetic circuit would likely have cost millions of dollars. And Injector Dynamics is a profitable company, not that profitable, right? So what we found is that there were a couple of pieces of that circuit that we could manufacture out of a different material and get the magnetic strength that we needed to get the job done, so to speak. And I mean, I can go into more detail about it, but essentially what we do is we manufacture a few of those pieces. We perform some modifications to a stock valve to increase the flow through the valve, make a portion of the magnetic circuit, and then send that to Bosch, which gets built into the injectors. And of everything I've done in business, probably the thing that I'm most proud of is the fact that we've earned that relationship with a company like Bosch.
I can't imagine that would be easy to earn their trust. And I don't know about Bosch, but a lot of the OE manufacturers, I mean, the products that the scale of their operation for OE supporting the OEs is so dramatic that literally the aftermarket is such a drop in the ocean that no one really wants to bother. And I can imagine it might be the same for Bosch in this instance. So the fact that you've got that relationship is definitely a credit to you.
Well, that helps illustrate the thing that I'm most proud of. And what I mean by that is Injector Dynamics doesn't now and has never had enough money to go knock on their door and say, hey, pay attention to us. We've got a big bag of money, right? I mean, the biggest bag of money I could show up on their doorstep with is a rounding error to them. The way we earn that relationship is through engineering prowess. What I mean by that is Bosch is an engineering company ultimately, and we had to prove to the engineers there that we were not going to give them a black eye and that we were capable of engineering these products at their level. And maybe that's not fair to say at their level, maybe more appropriate to say at a level that they respected enough to let us play the game with them. And everybody will tell you that their business is the best. It's this, it's that. I never do that, but I will say that in this instance, we've earned that, and I'm very proud that we've earned that. And we've got our T-shirts printed up with Injector Dynamics on it. It's got Bosch Motorsport on the sleeve, and I'm always very proud to display that.
Absolutely.
And tell people that we've earned that relationship. So That's the bragging that you're going to get from me tonight.
Fair. Now, I want to dive into one of the products that you've had that actually was a little problematic, which is what is now quite an old injector, the ID 2000. Now,
Hmm.
from what I understand, that originally, as Bosch intended, and it was a Bosch production part, intended as a CNG or LPG
That's
injector,
correct.
is it correct?
Yep. Yep.
So that worked because it was a nice, at the time, probably the biggest flowing injector, and that's great if we want to make a lot of power. And as it sort of came into production and more people were using it, some problems were found around its performance with a fuel additive called MTBE. Am I correct in that?
Yes,
So
that's correct.
can you give us the sort of short story on what went on there and how you had to deal with that?
Yeah. So the short story is that all the other injectors have an all metal valve and an all metal valve seat. The what was the ID 2000 has a metal valve seat, and the valve itself is metal, but it has a rubber tip. And the reason it has a rubber tip is that it was meant to seal gases, not liquids. And of course, having a tip or a valve that's somewhat compliant allows it to hold pressure. It's a pretty impressive material, but there are a couple of ethers that just drive it crazy. Now, the valve lift in that injector is in the neighborhood of, going from memory, about 4.5 thousandths of an inch,
Hmm.
meaning from fully open to fully closed. So that rubber tip doesn't have to swell much before it shuts off half the flow. Literally 2 thousandths of an inch of swelling is enough to do that. And so that was one problem with the injector. The other was corrosion resistance. The reason for that is that some of the materials inside that make up the injector were different, and Bosch was rightly unhappy with us for having any involvement with that injector. But what happened is we made the argument that people are going to use these, whether anybody likes it or not. Let's give them something that works, so they stop wanting to use this. And that turned into a development process that went about, I think, about a year and a half to come up with a 2600, where we came up with an injector that had better corrosion resistance, that Bosch certified for use with liquid fuels. That's an important point to make. That injector, the ID 2600, is certified for use with liquid fuels. However, it's still not MTBE compatible.
Okay.
We worked with that. We couldn't make it happen, and it's a shame because MTBE is a great component for fuel. We simply couldn't make it happen. But the point is, there were numerous other improvements made inside of the injector, and it is certified for use with liquid fuels, unlike the ID 2000, which caused them a great deal of grief.
I think Bosch are quite vocal in their not supporting the use of that on anything liquid, aren't they?
That's correct. And the most important thing to Bosch as a company is their reputation.
Mm.
And I understand that because I feel the same way. The most important thing for Injector Dynamics is our reputation. If they see a product being used in a way that makes it appear that their product is less than stellar, they're not happy about it, and rightly so.
Understandable.
And so the answer ended up being, let's give people something that does work. And there's so many talented people there, and somehow we got their attention and we worked together on it, and we have a product that not only flows more but is far less likely to suffer from internal corrosion issues for use with alcohol fuels.
Coming back to MTBE, what fuels will we find that additive in?
MTBE has been outlawed from any of our basic transportation fuels in the US because we have a very old infrastructure for moving fuels, and it's prone to leakage. And MTBE tends to seep into groundwater and contaminate things. Now, in Europe, they don't have that problem. They have not outlawed MTBE. So, as far as I know, in most of Europe, MTBE is still in the pump gas there. However, we build products for race cars, so I don't know that I care what's in the pump gas, right? This is all about racing. I believe that when I was in Spain, I could smell it. I believe they still use MTBE in their pump gas, but again, that's pump gas. Now, back to race gas, it's still common in many race fuels, and it's important to find out whether or not it's in that fuel. Any of the manufacturers will tell you. My friends at VP Racing Fuels here in the U.S. love to use MTBE because it's just a really good chemical, right?
Mm.
and they make it relatively clear. So VP Import, MS-109. Actually, I should know the answer to this. I'm sorry, I don't. They have probably half a dozen fuels that use MTBE, and the ID 2600 is not compatible with those fuels.
Okay, so the takeaway essentially is understand what is in the fuel that you
Yes.
intend to run. Make sure there is compatibility there. This is a known problem. Stay away from it. In terms of the rest of the injectors, the 1050, 1300, 1700, how do they handle MTBE?
So the joke and the truth is that those injectors are compatible with everything but dirt.
Okay. All right. So there's options there, albeit if you need a huge amount of flow, problematic options potentially. If you need to run on a fuel with MTBE in it.
Typically, if you need very high flow and you're using the 2600, you're running an alcohol-based fuel. There are not many people, or nobody that I know of, that's mixing MTBE with either ethanol or methanol. And the corrosion resistance of both of those fuels in the 2600 is exceptional.
Okay, perfect. All right, Paul, I think we'll start to move on and wrap this thing up because we are going a bit long here, and I do want to respect your time. We've got...
Oh, wow. We have. I'm
we
fine
have.
with that, but yeah. Sorry.
We've got the same three questions that we like to wrap up with here and ask all of our guests. And the first of those I'll throw at you. What's next and in the future for you and Injector Dynamics? Anything sort of on the horizon, new and exciting that you want to share with us?
Big picture. We used to be an injector company. We now see ourselves as a fuel supply company, right? So we're now interested in everything from the fuel tank to the tip of the injector.
Mm-hmm.
There are numerous products that we haven't talked about now related to some of our fuel filters, our high flow fuel pumps. We are tomorrow or the next day releasing an entire line of UTV specific fuel systems. So our work on fuel systems, including fuel rails, some with integral pulsation dampers, fuel pumps, fuel filters, all that's going to grow in the future. Everything related to getting fuel into your engine is now what we consider something that we need to work on. And the way that we work on those, to be clear, is that, Tony builds race cars all the time. If we were on camera, I could walk you through my shop. There are 12 UTVs here, right? Running in all various types of racing. We are constantly, as a company, building race cars. And so when you build a race car, you got to buy parts. And we buy a lot of parts that make us say, wow, we could probably do this better. And maybe I shouldn't put it that way, but if we see a hole in the market, if we say, boy, there's something missing here, there's something that's very hard to do or very hard to do well, or possibly it's not being done well at all, and we can fill that void, that's what we intend to do. So that's big picture for us.
Fortunately for you, I think there's a lot of that situation in the market, either products that don't exist at all or are being done currently horribly. So yeah, plenty of potential there. One thing I am interested in, which we haven't touched on at all, direct injectors. It's sort of a market where, there are some aftermarket options, but certainly nothing to the degree that we see in the port injector world. And direct injected engines, of course, are becoming the norm, or maybe I should say have already become the norm. Is this an area you've got any intention to move into?
We did, and then we changed our mind. There are numerous reasons for us changing our mind, but the biggest being that the power potential of a direct injected engine is limited by the very short duty cycle that you have available to inject fuel. So previously, they said the induction cycle lasts for 25% of a complete cycle. Well, you can extend beyond that. You can inject maybe 30% duty cycle, but you're very limited by that. You're very limited in the size of the injectors that are available. And so we talked before about how with port injectors, spray targeting is far less important than you might think it is. The opposite is true in direct injection. It's everything. And every vehicle is very different. Every vehicle has a very unique injector designed around a piston shape, or designed around its location, designed around the shape of the combustion chamber. And while we make 4 injectors essentially now that fit nearly every vehicle on the planet, that would not be the case with direct injection. So we could be looking at spending hundreds of thousands of dollars. I mean, it's way into 6 digits to develop a new injector. Now imagine having to do that for every vehicle on the market. So even if we could afford to do that, we would find that the power would still be limited by the architecture of direct injection.
And I think ultimately everyone in the DI world has kind of come to that same conclusion, and now those who want to make mega horsepower on those applications are simply adding port injection back into the mix anyway. Either it's already there from the factory, or there's aftermarket options to add a spacer plate into the inlet manifold and bang a set of port injectors in as well.
Well, and it's worth noting that the manufacturers are now often adding port injection to their direct injected vehicles. You're seeing that more and more dual fuel systems. My last conversation with a friend at Bosch who was handling that stuff was that they definitely promote that because they think it offers the best of both worlds. So remember, direct injection was the result of meeting some relatively stringent emissions requirements, and like any new technology, it brought its own problems with it. It has limitations. As it turns out, a dual fuel system, at least with existing technology, is ideal, and it ends up being ideal for the aftermarket as well. Let the direct injection do what it's good for, add port injection for making big power. So I don't think we'll end up, we thought we might go back and address it later once the technology had matured. I don't see that happening at this point.
Perfect. All right, Paul, our next question. Have you got any advice to maybe impart on our listeners, or any advice you'd give to a younger version of yourself based on your experience to date that would help maybe fast track your career progress, maybe circumvent some problems you've had, or anything that would help get to where you are faster?
I'm going to go off track just briefly and tell you that I think it would be great if someone had a podcast where they brought on business owners and instead of discussing their successes, discuss everything that they've done wrong. I'm not kidding. I'm not kidding. I think that would be a tremendous benefit to people.
I don't disagree.
But back to your question, it kind of depends on what people want to do. So if they want to be a tuner, the advice is different than if they want to own a business. But in either case, I think something that is critically important is simply to do a good job, right? Don't half-ass things. I don't care if you're a tuner or a business owner or a husband or whatever you want it to be. If you want to do something, focus on being good at it.
Yeah.
I don't care if you're a tuner or you're washing cars, just be good at it. Because if you're not, well, ultimately your life is just going to suck. I mean, I know that's not really the direct answer to the question you're asking, but if you want to be a tuner or you want to own a business in the performance aftermarket, you have to focus on turning out a quality product above all else. Nothing else really matters. They come and go all the time.
I think that's actually is really solid advice. And I mean, we've had similar guests say similar on the podcast before. I mean, coming back to your first point about failed businesses, you know, it's not being said in jest. I think it's fair to say that we learn more from our failures than we do from our successes. So, you know, it's a necessary part of life. Unfortunately, it hurts at the time, but you know, we progress, we learn, and we move on. And I think increasingly these days, in terms of turning out a good quality product or doing a good job, people want to take shortcuts and aren't prepared to put in the hard yards. And unfortunately, that is in 99.9% of circumstances just a necessary stepping stone to get to ultimate success. So you can't short track that, or at least very few people will and will get away with it. This industry is very, very tight, close knit, and if you're turning out poor work, not doing your job properly, that reputation is going to stick with you. It's very hard to break that.
So do you know why High Performance Academy is successful?
Well, I'd like to think it's because we're providing a quality product that people actually see value in.
Every once in a while, I catch little bits and pieces of what you're doing, and I swear, well, I'm going to say it. Everybody's going to think I'm saying it because I'm on the podcast. I've never once watched one of your videos and spilled my coffee and screamed, "That's bullshit." and I can't tell you how often I do that. I mean, it just, you're not putting crap out there.
Which
and I know I'm on your show. Of course, I'm supposed to say that. You've earned your position by turning out quality. You were doing that before High Performance Academy when you were building cars. And so if anybody wants some advice, look at people who have been successful for an extended period of time and note that they all have that in common. you know what? I've got one other thing, focus. You got to be focused on what you're doing, right? But that's kind of secondary because if you're focused on doing a shitty job, well, you might not be around very long.
That actually sort of goes full circle back to one of the things you mentioned at the start of this chat, though, was if you didn't have a business partner, you'd sort of be chasing the next idea. And
Hmm.
I think that comes to that focus. It's very, very easy, no matter what you're doing in business, to sort of get, something up and running and it's working and you kind of get bored with it. And then you start chasing that new shiny object. And that's sort of a syndrome. I suffer from it myself. And it's good to be sort of surrounded by other people that, no, let's just get back on track with the thing that we know is working. Let's just
Yeah.
keep down this track. And, that focus and sort of seeing it through to fruition, that's what's going to see success, rather than starting down one path, getting it half built. Nah, I'm bored with that. Let's go over in this direction. And you kind of do this 10 times and you've just built nothing, and nothing's really working.
The internet has reduced the cost of entry, meaning anybody can be in business now. It costs almost nothing to put together a website and start cranking out some parts. The guys who are going to stick around are the ones who turn out a quality product.
Absolutely. All right, Paul, last question. If people want to follow you, see your products, see what you're up to, where are they best to do so?
Well, we lost control of our old Instagram page, and it's just a mess. We started a new Instagram page. I don't think there's a great deal of stuff on there yet, but we're working on that. I left Facebook a few years ago because I'm too grumpy to be there. So you can't find me there. And as a result of me not being there, I don't even know what the Injector Dynamics Facebook page looks like. So this is not a dead end. Here's what's important. We do have a website that has good information. We're not that active on social media because, quite frankly, we're busy trying to turn out a good product and not trying to, get people's attention. So check out the website, injectordynamics.com. Find Injector Dynamics on Instagram. If you want to find me on Instagram and see pictures of random things around the shop and my child doing silly things, you can find me, the real Yaw Power, on Instagram. But we're not a marketing company. We provide products and solutions, right? So if you want to find us, call us, send us an email, right? Because quite frankly, Instagram, Facebook, all of that is just pictures and words.
Well, we'll put some links in the show notes to those pictures and words anyway, and make
Okay.
it super easy for people to reach out however they prefer to do so. Look, Paul, I think you've won the non-existent award for longest podcast, at least at this point, but it has been a pleasure and it's been a goldmine of information. I hope everyone listening who's made it this far has enjoyed it and got as much out of it as I have, so we really appreciate your time.
Yes, I hope everybody got something useful. That's my intent when I do these.
Perfect. Well, we'll leave it there, and I look forward to actually catching up in person in the hopefully not too distant future. Thanks, Paul. If you enjoyed this episode of Tuned In with Paul Yaw, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt anywhere in the world. Also, this is a great place to ask any questions you might have, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to The Real Loodle from the United States, who has said, great podcast to listen to while working. I love listening to this while in the shop, especially when I don't feel like listening to music. Thanks for your feedback there. Get in touch with us with your t-shirt size and shipping details, and we'll fire a fresh tee straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.